Hi. To verify the convergence of a numerical series, you should follow an apparently simple algorithm. First, you should calculate partial sums as n for generic n. And second, you should discuss existence and value of the limit for n going to plus infinity of partial sums as n. If this limit is finite, the series is convergent, and the limit provides the value for the sum. If the limit is infinite, the series is divergent, while if the limit does not exist, the series is indeterminate. The problem is that, in general, it is very difficult, if not sometimes impossible, to calculate partial sums in a way that allows us to compute the limit. So a natural question arises whether there is another way to determine if a series is convergent or not that does not require to compute partial sums and to discuss exactly the limit of partial sums. The comparison test, which is, by the way, the mother of all convergence tests, provides an answer to this question. In this video, we will see this test, how it works, what are the main features, together with some examples. The starting point is numerical series with terms of constant sign. For clarity here, we will assume that all terms are positive, but the results hold similarly for series with negative terms. The key remark is that in this case, we can notice that if we write the sum Sn plus 1, this is equal to the sum Sn plus the term an plus 1. And being this last positive, we realize that Sn plus 1 is larger than Sn. So in particular, the sequence of partial sums is increasing with n. As with all monotonic sequences, the limit of Sn exists whether finite or infinite. In the first case, the series is convergent. In the second case, the series is divergent. In other words, a constant sign term series cannot be indeterminate. Therefore, to show that the series is convergent, it is sufficient to show that partial sums are bounded. In this way, the limit of partial sums cannot be equal to plus infinity. It is on this idea that is based the comparison test. Let's see the precise statement. Suppose that we have a sequence an of positive terms. This will be the general term of our series, which is dominated above by a certain other sequence bn, at least for n larger, and such that the sum of bn is finite, so the series of bn is convergent. We say that this series is a convergent dominant for the series of the an. The fact is that if these two conditions holds, then also the series of an is convergent. The reason why this is true is intuitively very easy, because if the a's are smaller than the b's and the sum of the b's is finite, then also the sum of the a's will be finite. In the practical use, with a given series sum of an with positive term, we look for another series with general term bn with a known behavior. Known means that we know that the series is convergent, that dominates the series an. In particular, important examples of comparing series are the harmonic series, sums of 1 over n2 alpha, that converges if and only if this parameter alpha is greater than 1, and geometric series, sum of powers of a number q, here assumed to be positive because we want a constant sign term series, and in this case this is convergent if and only if that q is strictly less than 1. We have to be careful because it looks easy, but it is not easy at all, in the sense that it is easy to estimate, to bound up from above some an, but the problem is that we may get a divergent dominant, and in that case it is completely useless. So let's see some examples how it works. Here we have this series, the sum of n factorial divided n to the n, for n going from 1 to plus infinity. Clearly we have a positive term series. So we may notice also that if we write an as n factorial is the product of all integers between 1 and n, divided n to n, which is the product of n times itself n times. Now, if we just save these first two fractions, we may notice that all the remaining fractions have a numerator which is smaller than the denominator. So this box is just less or equal than 1. So we may say that that an is less or equal than 2 over n squared, which is the term bn, the general term bn of an harmonic-like series with exponent 2 greater than 1. So it is a convergent series. So Bn is a convergent dominant for An, and therefore the series of An is convergent because of the comparison test. Let's look now at a second example. Here we have the series sum of 2 to exponent minus root of n. It looks like a geometric series, but it is not a geometric series. However, we may think that it could be natural to compare this one with the geometric series. So we may wonder if there exists a q that will be positive and less than 1 in particular, strictly less than 1, such that 2 to exponent minus root of n can be controlled above from q to the n. Now, I leave to you to think about this question to see if this is possible, and in the case with which value of q. Here we follow a different way, which is the following. We try to compare again 2 to minus root of n with the general term of an harmonic convergent series, so something like 1 over n squared. So we wonder if this is true at least for n big. Now we cannot solve directly this inequality because it is not an elementary inequality, but we can arrive to answer to this question indirectly in this way. So we may notice that this is equivalent of saying that n squared 2 to minus root of n must be less or equal than 1, at least for n big. Now the idea is that if this quantity goes to 0 when n goes to plus infinity, for n large, this quantity will be clearly less or equal than 1. So the point is, let's go to compute that limit. And to compute that limit, we observe that if I take n squared 2 to minus root of n, and I put also the square as an exponential, so I write this as 2 log base 2 of n squared times 2 to minus root of n. This becomes equal to a unique exponential with exponent 2 log base 2 of n minus root of n. Now, root of n is a power, and exponent 1/2, that dominates the log at infinity because of the comparison logarithm versus powers. So the exponent here clearly goes to minus infinity, and therefore the exponential will go to 0. Here we are, because you see that the limit of this quantity is 0, and therefore it will be less than 1, at least for n bigger than some capital N. In particular, we can say that this series, the harmonic series with the general term 1 over n squared, dominates the proposed series, and therefore by convergence theorem, we can conclude that also this series is convergent. The comparison theorem also works in reverse. Let's see what does it mean. If a given sequence an, this is bounded from below now by another sequence bn, positive, at least for n large, and such that the sum of bn is a divergent series, then also the sum of an will be a divergent series. Again, the idea is very natural. If the sum of the b's is infinite and the b's are less than the a's, well, you understand that the sum of the a's will be infinite as well. That's all for now. What can you do next? Well, first of all, you should practice the comparison test on exercises similar to those we have seen in this video. And then if you want to have a more deep understanding, you should try to challenge yourself on proving some abstract property. Here we have an example. You have a series with positive terms, an, and you have to show that this series is convergent if and only if this other series made of terms an divided 1 plus an is convergent. You don't have to think to any specific an here, but just to a generic an. One way, this way, is relatively easy. The other way is a little bit more difficult. So good luck and happy studying.